This is the large breadboard. It has quite a few nodes. You know, these are all nodes and quite a few buses. And we'll show you how we're going to set this up. The supplies that relate to breadboarding, you can see you've got some pre-cut jumper wires, and they're nice to use at times. I mean, you can always cut your own. We have solid wire in a little box here. Make sure that your box says SLD, solid, instead of stranded. Every now and then they ship the wrong thing, and for breadboarding it's not really easy to use stranded wire. You need solid wire. So make sure that that's the case. It's 22 gauge, so it's good for breadboarding. And you have some other jumpers included. You can see these are tend to be the more high quality jumpers. So you can see the little square, plastic. So they're a little better quality. These come with the Arduino bundle, so you have these also, but just be aware, these have been known to fail. These are you can tell them apart because this has the round, sort of a round plastic termination. And I mean, you can still use them. Just if your circuit's not working, that's maybe one of the first things to check, that your jumpers are all okay. You can just check them with an ohm meter from one end to the other, and if you wiggle the wire and you find that your ohm meter's flickering, the wire's bad perhaps. But those are all good options when it comes to breadboarding. You'll see if it's just a temporary circuit that you're trying to do. Maybe then you do use something like these jumpers, and the circuit tends to be sort of a little harder to follow. You got like long wires all over the place. If it's something that's going to be a little, semi-permanent, where you're going to use the circuit for a while, it's well worth the time to cut your wires to length and try to make the circuit as neat as possible instead of the whole spaghetti look. And of course you can use these that are pre-cut to lengths, but the only thing about the pre-cut ones, you don't get to pick the color. So for a given length, you're stuck with a certain color. So if you want, to do a neat layout that's color oriented by certain colors and lengths, here you go. You can cut it off with it. Okay, so there's lots of wiring options. I think the first thing we'll do is show you how to get these posts onto your board. It's pretty simple. Just notice the flat spot in each of these. That's important. So let's get those posts out. Here they are. These 4 posts are going to go here. And then there's 5 little feet that just stick on the back. And I mean, you can arrange them, like the number 5 on a dice. That'll work. So let's go ahead and put these posts on. And we'll take that little nut off, of course. Drop that one plastic washer off. And then this is the part that goes on. Now, we mentioned to orient that flat spot is important. So you've got a flat spot here, and that's going to fit. If we can get you see there's a flat spot right on the plastic there. Okay, so that's important that lines up. That helps the post not spin. It kind of locks it in place. So we're going to do that. And you can tell when you've got it right from the back side. You can see that I'm going to put that flat spot right in there. There we go, like so. And then we're going to put the back washer on, and it's just the piece of plastic. One important thing to say about that, make sure the flat side of that plastic washer goes against the breadboard, okay? And so it should go on like that. And let me see if I can show you. This is also important to make sure things tighten up properly. I mean, the other side of that plastic, if I can get the light on there, right? There you go. You can see there's like little, there you go. It looks like a little nut. Make sure that nut's facing out, just like so, okay? I mean, I can show you the problem. If I didn't do that, if I put the nut in, look what happens. If I you don't want the back washer to fill in the hole that the binding post needs to go into to lock itself in place. So the thing is, they made this metal thinner over time. That used to be the way to assemble it, but not now. Not with the thinner metal, because there's not enough thickness there. So don't do it that way. Don't fill in that hole. Put the flat washer flat like that. And you see, now I've got metal to help lock the binding post. That's just so the binding post doesn't spin, you know, on its own accidentally. So that's how we want to do it, just like that. And you can see the nut just goes on the back then too. And you can see, again, the orientation of that plastic washer on the back. The flat side of the plastic washer is against the metal breadboard. Okay. And when you put the nut on, you know, if you lose track of where the flat spot is on the post here, you can always wiggle it back and forth. And you'll feel when it's dropped in and can't turn. So you should have that plastic flat bumping in, right in, seating in with the flat of the metal, and then this won't be able to twist. If it can spin, it's not dropped down in. So you can find it again if you've lost it just by doing that. You know, spin this around a little bit until you feel it drop in place. And then once you have it seated, that's when you can just go around the back and tighten up the nut. If you happen to have a nut driver, that's great. You can use that. Otherwise, a little adjustable wrench will work just fine too. So just get in on that and tighten that thing up. And here you can tell, again, if you have it seated, that flat spot, if it's lined up with the metal, it'll hold itself from turning. So you can just, don't go too crazy. These are just plastic parts. So you want to torque on it a little bit so it, you know, it gets nice and snug, but don't overdo it. Okay. So if it's all done properly, that binding post is nice and secure. And the reason we go to that level of detail to explain all that is there's nothing more frustrating than when you're trying to clamp a wire down and you go to tighten it, and the thing that happens is the whole post just spins on you. It's super annoying, and it's hard to tighten anything down then. So that's why we go to all those lengths to show that. Another thing I might mention when you're putting those posts in place, you might have noticed I had this plastic nut on top. I had it unscrewed because I don't want to be tempted to hold onto the post like this and torque the back nut. I've seen people do that. They didn't have the binding post seated in that slot, in that flat spot, and then they were grabbing on here to this knurled knob while they were, you know, torquing down this nut. And what happens is you're trying to put some tension on the threads here, but those metal threads will way outcompete the plastic threads of this knurled knob. So what happens is, if you hold on here to hold it still, if you try, because you're not seated in the flat spot, and you're also, this isn't opened up, you're using the plastic threads here to hold on to it and match what you're trying to torque with metal threads here, and the plastic threads strip. And once you've stripped the binding post, you can just throw it in the trash. It's no good anymore, because we rely on these plastic threads to clamp down on a wire that can be put through sort of the center hole. If I can get this so you can see it, you know, but there's a little hole down the middle. You can put a wire in there and then clamp down on it with the plastic, but not if the plastic threads are stripped. So be cautious. And when you are clamping down on wires, again, remind yourself that it's just plastic threads here. So don't over tighten. Don't go too crazy. I mean, they're strong plastic threads, and just give it a nice little finger tight and you should be good to go. Okay. Okay, so I've got the rest of the binding posts mounted, and if I've done it correctly, there should be no wiggle at all in any of them, right? I'm trying to wiggle them, they're tight. I've torqued down the nut on the back sufficiently that they're going to hold firm. And also I can double check the fact that, you know, the threads, the plastic threads, none of the threads are stripped. I can go finger tight there with good clamping action. Notice the other thing that you've accomplished by torquing that back nut tight enough, it should be, those metal threads should be tighter than these plastic threads. So what happens is I can tighten down, and then when I go to loosen, I can loosen without undoing the back nut. That's also why that flat spot's there. It'll prevent you from loosening the back nut and the whole post starting to spin. So yeah, so check that all that's working, and we're good to go. These binding posts also can receive what's known as a banana jack on the top side. So you can put wires in underneath and clamp on them. You can also bring banana jacks right into the top. We want you to be able to power up this breadboard at home. So I've included a power supply for the large breadboard, and it should be in your box of parts that I sent you. So find this little box, and you'll see what you've got is a 5-volt power supply. And it's got some nice convenient stripped leads already, and they're tinned and ready to go. It's a 5-volt power supply. It can put out up to 1.2 amps. You can see the markings on there. That doesn't mean it's going to force 1.2 amps. It just means it's capable of delivering that. But Ohm's law will determine how much current actually flows. So, the decimal point's hard to see, but it's 1.2 amps. And it's 5 volts. It's a fixed 5 volts. And for all of your digital labs, that's the voltage you're going to need. So we kind of dedicate the large breadboard to be a sort of a 5-volt prototyping area. And some of the exercises that I'll do with you, I'll just make sure I keep it at 5 volts too, and that'll work out. The first thing we have to do is figure out which of these wires is the positive side of the 5 volts and which is the negative side. And the colors that we're going to use are standard. We'll put the positive wire to the red post and the negative side of the 5-volt supply to the black post. So we have to figure that out, and there is a difference in the wires. Let's see if you can see it. It's kind of subtle. One of them has a little bit of a white striping on it, and one does not. So we'll try to identify that, and then we'll know which wire to put where. And that sounds like we'll have to get our voltmeter involved. So we'll have to grab that out of the toolbox, and I'll show you a couple things on the voltmeter. This is the meter from our toolkit that we'll be using. It's called a digital multimeter because it can measure multiple things. And of course, for short, you just call it a DMM, digital multimeter. And we'll do a separate video on this, but we better introduce a couple things now because we actually need to check those wires from our power supply. So you can see the multimeter name. It earns its name. We can measure all kinds of things: volts AC, volts DC, frequency, temperature, ohms, resistance, capacitance, and then current. And it depends. If you have a high current, you'd put the selector switch here, 10 amps. Or if you're down in the milliamp range or down in the microamp range, you put the selector switch to the appropriate spot. And then there's a common lead here. It takes for everything except current. You're going to use these two jacks. The common is always the black lead, and it's the common for everything that you're doing. And then we've got this jack that we're going to use to measure. You can see voltage, current, capacitance, resistance, frequency, temperature. To measure low currents also over here, milliamps or microamps. The only time you use this jack, and you have to use this jack if you're up on the 10 amp scale, and that's what they try to show you here. So just a quick look at it. So let's try to set this thing up we just need it now just to check the voltage polarity, they would call it, when you're trying to find out which side is positive and which side is negative. That's called polarity, and that's what we need to find out. You have to get batteries in this thing, so you can just take the orange jacket off, and then there's a screw in the back, and you just take that screw out. I already loosened it here. So you pop the back off, and there you go. Just pop 2 AA batteries in. You know what? It ships with some El Cheapo ones. I usually just throw those in the trash. I don't want them leaking all over my meter when they do die. Get something with some quality. It'll last longer. You know, I don't know, Duracell, whatever. Pro cells, you know, tend to have maybe even a little more shelf life. Anyway, load it up with something a little better than maybe those ones that it ships with. Do yourself a favor. They'll last longer. And for future reference, but we'll do this in another video, maybe you can see these are your fuses. When you are using this thing as an ammeter, it has to protect itself somehow, you know, in case, you know, you're trying to measure more current than it can handle. Rather than have your meter, you know, melt down, it's protected. So there's a 500 milliamp fuse. It's for the low scales, and then like I think it's a 5 amp fuse for the high scale. So anyway, so that's where you would go to replace batteries or replace fuses for the meter. And then we'll button this thing back up, and we'll try to get some voltage checked out on that power supply. The meter comes with some test probes, and we're going to use something else. But here, if you wanted to use these, you just pop these little caps out, and then these would insert into your meter, and then you can probe. And of course, if you're on voltage, it'll just tell you the difference in voltage between these 2 points on the probes here. And it's always measuring the voltage at this point with reference to this point. There's some caps on there if you're coming into like some small spots and you don't want to short things out with your probe. You keep these plastic boots on, but you can also take those off. Hard to get off. And you get the full bare metal probe. So those are some probes that ship with the meter. We've also included in your toolkit some other options, and this would be one. It's a banana jack, and then it goes to a little pin. Great for probing a breadboard. You know, you would put the banana jack in, and you would have, of course, 2 of these. So you should have this in your toolkit as well. And look how nice that is. You've got pins that can go right into the breadboard if I want to look at voltages, you know, at the voltage between those 2 nodes. Real easy. So you have that as an option for your meter. And actually the option we're going to use right now is banana jack to mini grabber. That's this type of a probe. You just have a little mini hook there that you can push out and grab on to things. And so you just put that in like so, and we're all set to measure the voltage between these 2 clips. So we would set the selector switch to voltage, okay? And right now it's saying, you know, not really seeing much voltage, and that's not surprising. We don't really have a voltage source. In fact, if we connect them together, it'll show you no voltage exists, right? That's that 0 ohm path. How can you have voltage between 0 ohms? So across 0 ohms. Okay, so I'll plug in the power supply and we'll finally get to that. Let's check out that polarity of the power supply. Okay, so I've got the power supply plugged in. Notice I have these end wires pushed far apart. Be very careful not to let these 2 bump together. When the power supply is plugged in, you'll short out the power supply. I don't know if it'll survive that. So I'm just gonna take a guess. I have no idea, but I'll just hook these leads on and see what my reading is. Again, be sure you don't bump the wires. And I do not have the switch on. Hold on. All right. Let's see here. Okay, now we got something. Okay. Now, can you see, and again, just trying to keep those wires from, I don't want them bumping together. And you don't necessarily have to do this exercise because I'm doing it. Just making sure those wires don't bump. Okay, do you see that it's a negative? It's reading negative 5.13 volts, which is telling me that the voltage at the red lead is more negative than the voltage at the black lead, because the display is always going to display the voltage, the difference in voltage, and it's going to be what the voltage is at the red lead compared to the black lead. So the red lead, I mean, where I have the red probe, that point is 5.13 volts more negative than the other point. So that's the negative side of the supply. And if I want to just be certain that of everything, I mean, I can switch those, right? I'm going to put the red lead over to the other side of the supply and see how the negative symbol goes away. So it's telling me this wire is 5.13 volts more positive than this wire. So the wire that I have the red lead hooked onto is the positive side. Of course, make sure your banana jacks are oriented properly. This has to be the COM, and the black lead has to go in here, and the red lead has to go in there. Okay, so I proved that out. Let me get this turned off, and we'll look at which wire that is. So we have our answer. It is the wire with the white striping that is the positive side of the power supply. If you can see, it's just really faint, but just look for that white, a little bit of white striping. I can get it there. Okay, good. That's the positive, and the other one's the negative. So here's how we're going to bring power onto the breadboard. We're going to put the power supply, clamp it underneath those posts, and at the same time, we're going to take a red and a black wire and share underneath those posts, clamp both things. And these wires, you can cut some lengths from your box, and that's what's going to bring the 5 volts from the posts onto the board itself. To get started, just cut some lengths that are plenty long, and then we'll put them in place and cut them to length later. Strip one end of each wire here. Make sure you give plenty of strip length. I'll show you why in a minute. And these are already a nice amount of conductor showing. I actually used the second hole, not the 22 as marked, but the 20 gauge hole I think works pretty well. It is 22 gauge wire. This isn't exactly a calibrated scale, I don't think. And I like to use the largest hole that I can that still gets the insulation off easily. And that way I'm trying not to nick the conductor like we mentioned before. So I think, the 20 gauge hole works pretty well. So here's what you want to try to do. You've got the wire stripped, and of course you're going to clamp down on it with that binding post. But what you don't want to do is clamp on the insulation, because then you might have an intermittent connection. So make sure that you have enough strip length that you can see a little bit of the conductor on both sides of that binding post when you do clamp down. That gives you confidence that you did not clamp on the insulation. Clamping on the insulation just means you're not clamping on the conductor, and it might not be as good of a connection. So you're going to put the wire with the white striping in the red post. And what we're going to try to do here, maybe we can do it now, get both wires in there. So I have my power supply wire, and then I'm going to bring in my, wow, got to try to do this for you, but you can see what I'm trying to do, right? I'm going to take the 22 gauge solid wire that's going to bring the power to the breadboard. Again, I need another hand here, but this is what I'm going to try to do, right? Okay, so I think you get the idea. So I'm going to get both wires in there, and then I'm going to clamp down on both of them. And I feel like it's okay to do this because both wires are similar gauge. This would not work if we had drastically different gauges. I mean, you would pinch one but not the other. So, but this is the idea here. I think that it will be okay. So let's see if I can get that. So. And again, just keep an eye on those wires. You don't want to clamp on insulation. That could be trouble. So I'm making sure that it's, just trying to follow both of them at the same time. So yeah, let's get this done here for you. All right, so something like that. And then you can always inspect it and, adjust it. You don't want too much conductor showing. I mean, that just invites things to bump into it and short out and stuff. And I torqued down on that pretty good, twisted this pretty tight. And you can see from my final inspection, I feel confident. I didn't get any insulation underneath the clamping action, and so I see a little bit of conductor there. And I can see I also did not clamp here. I've got a little bit of conductor showing on my power supply lead coming in. And then of course I have a little excess there, and you can just use a flush cutters and just nip that off. You should have a little side cutter in there and trim that. Yep. Feel free to tug on the wires a little bit. Make sure they are indeed clamped. You know, like I said, I really torqued down on that pretty hard. Again, we're being so meticulous because you know, this has to last you for 2 years here, and the connectivity is one of the biggest troublemakers. You know, when you have a bad connection, just physically like this, that's one of the most common things that'll cause trouble. So trying to avoid that. And now I've got the negative side of the power supply secured, and same game there. And I'll do what's called dressing in these wires a little bit. I'm actually heading over to this corner of the breadboard with them, and so I'm not going to pull them straight across. You know, you give yourself a little bit of extra. Maybe it'll come in handy. You know, if you had to re-terminate something, then you could maybe pull it taut. But it's always good to have what might be called a service loop or something. Maybe we won't actually do a loop, but you know, don't pull things tight. Give them a little extra. It's always a good idea. And we're sort of dressing in the wires. We're heading over to this corner. That's probably where we'll bring them onto the board. So those are good to go. And then another thing to mention, this wire that's heading to the power supply, we really don't want to leave it just so that the binding posts are the only mechanical securing of that wire, because that's going to break eventually. I mean, that's if we rely on this point to hold our wire, and we're, you know, moving that around a lot, it'll wiggle back and forth right at the point there, and the wire could break, or it could just come loose. So what we want to do is strain relief this cable somehow, and I didn't have anything really that I could send you other than I had these little squares of Velcro, so maybe we can try that as a stopgap for now and just see if they're sticky enough. But what you would really want to do is put some kind of a sticky back fastener that maybe comes right on here. I looked for some, I don't have any, and then a zip tie, you know, would be great, you know, just so maybe you can find one at a hardware store if you get out or not, I don't know, but that would be perfect. That's what I was wishing I had, to actually zip tie that down. But let's do it with the little stickiness of Velcro, the back of it, you know, I'm thinking might do something for us. So I'm gonna try this little swatch here. Double-sided tape could work. I mean, this is, like I say, more of a stopgap than anything, but because the idea is, you know, you need to strain relief the power entry points. That's always a thing that you do. Okay. You know, we'll see how long that stays on, but at least it's something for now. So now we're going to bring this 5 volts actually onto the breadboard, and we're going to add a couple little features. We're going to put a little switch in place for you so that you can power off your breadboard without having to go unplug that power adapter out of the outlet physically. And then I'm also going to give you a polarity indicator with a little red LED and a little green LED. And the idea is that you can see the green LED will indicate that everything's okay, that the polarity of the 5 volts is correct, because we're going to make the red buses the positive side of the 5 volts, and we're going to make the blue buses, the blue bus the negative side. If somehow that got switched, the red light would light up and the green light would not. And the red LED will just be a warning to you, basically saying that the polarity has been reversed. And especially when you're doing digital labs, that's going to be something. If you see a red light, that just means do not put any of Schreiner's ICs on the board. They will explode. So let's go ahead and put these little indicator lights on the breadboard first. The pins as they are very short, so that's not going to be great for putting onto a breadboard. So what I want you to do is bend those pins like so. Just take them, and if you can, it's kind of hard to see, isn't it? If you can see this way, I'm going to take those pins and I'm going to bend them. And now I've got some long pins, much better for the breadboard. Okay, so bend them like that. And then we're going to put this red one in place. And we're going to use, I'll show you which nodes. We're going to use this node and this node for our indicator lights. So the very first 2 nodes on the board, nodes 1 and 2. And the way we're going to do it, notice the orientation here. If you can see, this is the long side here. That's going to go out, face out. You're going to have to hold your finger over the little LED to press it in place, because now that we bent those pins straight, it would just want to pop out of its little holder. So let me show you. I'm going to do this, and like I said, I'm going to insert those pins right in those two nodes like that. So let me get that in place for you. There you go, just like that. Breadboards are great, aren't they? Now these LEDs, they do have polarity, which means they light only in one direction. So they're very specific. One pin has to be positive and the other pin has to be negative, and then it will light. They also need a limit resistor. We're going to add that. I did not forget about that. But they cannot limit their own current like incandescent lamps can. So we have to control the current for them. Otherwise, they'll burn right up. Do not connect 5 volts straight to an LED. It'll be toast. So we'll put a resistor in there to help them out, limit the current for them. But the polarity of the LED, it is marked on there. I don't know if we have a chance at seeing that. Let's see, I don't know. It's very faint and hard to see. So I'll just maybe have to tell you what it is. But there's a little plus and minus. Yeah, it's going to be too hard to see here. There's a little plus and minus on there. And let me check that out, and I can point to it and tell you which is which. Okay, so for what it's worth, for the red LED, the positive side is here and the negative side is here. And what we're going to do is add a green indicator. We'll do the same thing. We'll take those leads and bend them out straight so that we have longer lead length to go into insert in the breadboard. Okay, so we've got that longer leads. We are not going to put the green LED in the same orientation, right? Because we want one to light with one polarity and we want the other one to light with the other polarity. So what we're going to do is spin it, and now they have opposite polarities, and just snug them right in there against each other. That should work. So that's how it should finally look for you. And we still have just enough space left on our node that we can make a connection here and here. I can bring that up a little bit closer for you. Yeah. So we still have ability to connect here and here. And if this node is positive and this node is negative, the green light will light. If it's the reverse polarity, this node is positive and this one negative, the red light will light, the red LED. So that's a good look there. You know, get that orientation right for your LEDs. We're just using the first two nodes. There you go. All right. Now we said that LEDs can't limit their own current. They would just burn up. So we're going to use a little resistor. And I know we haven't done component theory yet, but a little preview. I don't expect you to know what LEDs are exactly. I don't expect you to know what a resistor is. But this is an example of one. And in fact, you can probably see it's got 3 red stripes. And with resistors, they are color-coded. So turns out the color red is the number 2, represents the number 2. And 3 red stripes means we simply have 2, 2, 2. First, for this resistor, since it's just 3 bands, we've got, and I know there's a gold band on there too. We'll talk about what that is. That's a tolerance band. But the 3 red stripes tell us 2, 2, 2, and the first 2 2s are digits, and the third 2 is the multiplier. So it's 2, 2 times 10 to the second, or 2 more zeros. So what we have here is 2, 2, and 2 more zeros, 2,200, or 2.2 K ohms. So it's 2,200 ohms or 2.2 K ohms that we're going to use to limit the current for these little indicator lights. Okay, can't resist doing just a little bit of Ohm's law. So we have a 2.2 K ohm resistor. And the power supplies actually at school at the benches can go up to 30 volts. So we're trying to get this breadboard sort of universal so that even 30 volts is okay. Not for your digital ICs. They must stay at 5. But for other experiments maybe that you might want to do, as long as you don't have any of your digital circuits on the board at the time powered up. Okay, but they can go up to 30 volts. So my idea for this breadboard is that it can universally handle up to 30 volts. Now the power supplies might even go to 31 or 32, so you might have a maximum sort of, 32 volts or something. I'll tell you something about LEDs. We'll cover them in detail later, but they actually take a little bit of voltage away. So, if it's a red LED, it might take like 2 volts, knock 2 volts off. If it's a green LED, it might knock 3 volts off. So, you're really looking at minus 2 or 3 volts-ish, and we're just trying to ballpark this. So bottom line is power supplies might go that high. The LEDs will knock off some voltage, but we're going to try to cover ourselves for something around 30 volts. And if you have something like 30 volts being applied, that the resistor will actually have to step in and control the current. 30 volts will land across the resistor. And bear with me, I know we didn't do circuit analysis yet, but we got a power supply that could go that high. The LEDs are going to knock off a little bit of voltage. The resistor will have to handle a sort of a 30 volt scenario, somewhere 30 volts-ish. And so that's why we picked the 2.2K, because when you do Ohm's law, you got this voltage and this resistance, and what's the result? It's about 13.6 if you do it with your calculator, milliamps. Now, I also know that these LEDs can handle a current, a maximum current for these LEDs is 20 milliamps. So that's why I picked 2.2K, right? Because I know this, and I know I have to use a resistor to protect the LEDs. I know they can't handle more than 20, and so I'm using 2.2K so that I can get as much of a 30 volt system in place, and the LEDs will not see any more than 13.6 milliamps. Now, when 5 volts applied to the board, you'd still have the LEDs maybe knock off, maybe around 2 volts, who knows, somewhere around there, and that would only leave you with 3 volts then, with the resistance of 2.2K ohms, and so then the LEDs would only be lighting up with about 1.36 milliamps. So I tested that, and there's still enough illumination. That's still visible enough to see. So, but there would be the whole range, so the LEDs, can be illuminating anywhere from there to there as far as their current. One other thing to mention, because it's a great example of stuff we're working on in the worksheets, I picked this 2.2K resistor, but I have to know what size resistor. And again, I don't feel bad. I know if you're not following so easily, we haven't done any of this yet with component theory. But look, I pick a 2.2K resistor, but I also had to choose that size of that resistor is a 1/2 watt resistor. So this thing is, you can tell just by size. Size always indicates the wattage. And a 1/4 watt would be maybe, a lot thinner, and 1 watt's going to be a thicker resistor. But it's a 1/2 watt resistor, and I needed that because, look, what kind of power is this resistor going to have to dissipate? What kind of wattage will be the result? And we can see, right? It'd be V squared. A quick way to see that, V squared over R is going to be the wattage. So 30 volts squared divided by 2.2K. And that turns out to be 409 milliwatts. So you can see why I want a 1/2 watt, right? 500 milliwatts, that's the same thing as 1/2 watt, right? 0.5, right? 0.5 watts, 500 milliwatts. So I chose a 1/2 watt resistor. If I put a 1/4 watt resistor in there, that thing would get hot when 30 volts is across it. It would be fine when we just are applying 5 volts. But I wanted, again, to make this breadboard universal. So you can see a nice, I only go into this, to show you the practicality of what we're learning already. Ohm's law and power equation. For something as simple as a little indicator light for your breadboard, it all comes into play. You have to know what value resistor you need to limit current to below 20 milliamps in all the scenarios. And then, of course, don't leave it at that. Always remember about power so you don't burn that thing up. the resistor, I mean. So there you go. There's your 1/2 watt resistor. Will work just fine. It's going to see that wattage. You don't want to push all the way up to the 500 milliwatts. So this is a good margin, you know, to be working. So I really wanted to do that little bit of theory to show you just how practical and necessary what we're learning even in this first week and second week is. So there it is, nice application. So here's our resistor. We've sized it to 2.2K and 1/2 watt. We're going to use it to limit current for our indicator LEDs. And the way we're going to do that is just connect maybe the 0 volt side right to this first node. And remember, the LEDs themselves, they both share these two nodes. So the green one's connected to these two nodes, and so is the red one, but with opposite polarities. So I'm going to take this node here, and with my 2.2K resistor path, I'm going to, you know, make a connection, and I'll show you how then to make it a little neater. But this is what we're trying to accomplish here. We're trying to make a connection to the 0 volt rail. And I guess I didn't mention, but that black wire, we're going to terminate that right on this blue rail here. Okay. All right, let's do that. So I've decided on a vertical mounting scheme for this 2.2K resistor. It's a little bit long, you know, to get there, so I'm going to turn it up vertically, and we'll take the one end of the resistor. I'm going to cut it to that 1/4 inch length, you know, that inserts into a breadboard well. So I'm going to nip that off. And you can always check that you have the right length. It's pretty easy. You can put it right beside the breadboard and see, you know, how deep it goes, right? So right along the side of the breadboard tells you how deep. But yeah, so I'm going to do that, and then I'm going to take this other lead, and I'm going to use it to sort of work my way over to the node that I have to get to where the LEDs are. So, you know, some kind of little creative bending, something like this probably. And I guess I should have mentioned, you have a box of these resistors that you can search for the 2.2K, the one with the 3 red stripes. Maybe I'll get that box to show you quick. So here's the box that you can find your 2.2K resistor in. And while you're setting up your workspace, it's probably worth, if you can get an organizer of some kind, or just be real careful not to let these get splattered all over the place. It's a pain trying to find the resistor you want later on if you haven't kept them maybe a little bit neat at least. But the bags are all labeled, so you can go right in there. I think I found it already, but I got to be careful. I don't want to make a big mess that I can never find them again. But it's in one of these bags, it looks like. They do give you a range. That particular compartment, it's got to be in there. You have 5 of every value, so try not to lose them. And I think what we'll probably wind up doing is the ones you use most often, sometimes people like stage them somewhere, either in a organizer or even, I don't know, on a breadboard maybe even. But okay, so that's where you can find the 2.2K resistor. And I think I got mine sort of tailored for what I want to do, sort of a little creative bending and stuff. And that's going to be my connection from the 0 volt rail, which is the blue bus. I'm just trying to get it to bring that over to the one node right there, if you can see. Okay, so see if you can get that accomplished. Again, make sure that you have long enough length on the resistor. You don't want to cut things too short, so the lead length is important. And of course, sometimes, I mean, you have a little needle nose. That's a nice tool for putting things in and out. But yeah, things should come in and out nice and straight, like we talked about on the breadboard. See how easy that is for me to insert or remove. You can just do that all day long, so without causing trouble. So that's when you know you got the bends all right and the length right and everything. So okay, so it drops right in there. I can terminate the 0 volt side of the power supply as well while I'm thinking about the 0 volt side. And you know what I think I'm going to do? I don't really feel like running this wire all the way over to here. There's no real need as I can see for that. So I'm going to take this 0 volt side of the power supply, straight across and just insert it right here. Remember, this blue stripe just means they're all connected. This bus, it doesn't matter where I connect on here, they're all the same point electrically. So I'm just going to do that. And notice where I'm going to cut here. I know my insertion point is here, and so I'm going to cut like a 1/4 inch past that because I know the insertion length that I'm looking for is a 1/4 inch. So there I have it cut and stripped. And, you know, sooner have a little more length than not enough, you know, so that's one little piece of advice there. But now we can just bend that and insert it and then sort of dress things in. See how easy, just nice and straight, you know. And like I said, I have a little more length. I figured I would. You know what else I noticed? I have a little too much length on the conductor, so that's easily taken care of, right? Just pop that out, nip it a little bit. I just don't like it sticking up more than it should. And then in it goes, and then just kind of dress it in. Whatever excess length you have can just sort of flow down in there and so on. You want to keep it a low profile. You don't want wires looping over here. Inevitably, you're going to snag it with a finger or a tool or something, or, you know, when you're trying to build your circuit, it's going to get bumped and get knocked out. And then it's easy to spend half a day wondering what's wrong with your circuit when you just lost power, that's all. So now we've got the 0-volt side of the power supply connected to the bus, and we've also got our indicator LEDs also connected to the 0-volt side through a current limiting resistor. And another nice introduction to components, well, we're going to use a little switch, and we'll get to looking at them in more detail, but a switch is fairly simple. It's just pieces of metal that get connected by an actuator. So when this is a slide switch, so when it's down, these two are connected, and when it's up to the other position, when it's in that position, these two are connected. Now we don't need both sets of contacts, so we're actually just going to use these two. And we're going to use these two connections, these two contacts, to connect the positive side of the supply to the breadboard, or not connected. So it'll be connected, not connected. We don't even need this pin, but we're not going to cut it off. It gives us nice security, strength as far as insertion. It'll stay put, help the switch stay put. And speaking of that, don't put this switch, don't put it anywhere on your breadboard. It does tend to ruin the holes on your breadboard, because these pins are a little bit large, but I picked that on purpose because then this switch stays put nicely for you. But I wouldn't just randomly put it all over the breadboard. I have other slide switches for that are the right thickness of pin. So just be careful. Just put it in one time and leave it there. And where we're going to go with it is right below the green indicator light, and we're going to put it dead center of the node. So you know you have those 5 insertion points per node. Just go right in the middle one, so there should be 2 holes on either side of this switch, and that'll allow us a good spot. And see, notice where I'm lined up. I think right at the green LED. I think I can, go right up against it. So I'll try to get a side view for you. If you can see it, the topmost pin of this slide switch here is right up in the center of the 3rd node, right up on that 3rd node, so right below that green switch. And it'll take a little bit of insertion force because you got to kind of stretch through that plastic. It's not really meant to be that wide, but the beauty of that is once it's in place, it'll stay there nicely for you. It won't pop out, and it'll be a nice little power switch for your breadboard. So there it is. And notice it's important that you put it in the center, because I'm going to need to make connections to those nodes on either side of the switch. The middle pin of the slide switch is right on node 5, and that's where I brought in the 5-volt side of the 5-volt supply, the positive side of the 5-volt supply. Terminated it right on the middle pin of that switch, node 5. We are almost done. And to make life easy, maybe we'll use some pre-cut jumpers. I mean, you can cut your own wires and strip them and fit them in there, but if you want to keep sort of a certain color scheme going, or if you don't mind random colors, pre-cut jumpers, they're very quick and easy. The things we have to do yet now are take the positive side of the 5-volt supply that's brought here, and to the middle pin of the switch, and we need to connect the upper pin of the switch, then up to the positive bus up here. And that way, when the switch is in the up position, our breadboard is powered up, at least these rails here. I mean, that's what we're attempting to do, to make it so that you can have these rails be powered up with 5 volts or not when the switch is down. So we'll just use little pre-cut jumpers, and I'll show you one more thing that we want to do is I thought of adding a little resettable fuse, and that's what this device is here. It's a thermal fuse. It can actually it can handle half an amp, 500 milliamps all day long. That's known as the holding current. If you get past 1 amp, that's what'll trip it, and it'll open up and from heat. So that's why it's a thermal fuse, but it's resettable. It automatically resets. When it cools down, it'll reset itself. So I thought we can give it a try. It does have some internal resistance, and I don't think that'll be a problem. We'll keep an eye on it. If we feel like we need to, not use it, we don't have to use it. I just think it's a nice safeguard if you have a short circuit on your breadboard. This little thermal fuse will go a long way to protecting the actual power supply. And you can see I've kind of matched it up where the power supply can deliver 1.2 amps without getting into trouble. And this fuse is going to blow, or not blow, it'll open, it'll shut the circuit off at 1 amp. So it's a good choice to protect this power supply. And like I said, it'll do half an amp all day long, and that's the carry current. So as long as our circuits don't go above half an amp, and as long as the resistance of the fuse itself doesn't cause problems, we can use it. So I think it's worth a try. So here we go to put the last pieces of the puzzle in place, and needle nose come in real handy for these pre-cut jumpers. The upper pin of the switch is at node 3, so I'm just putting a little jumper in here to get me over to another node where I have it, because I need more connectivity than just that 1 point offers. So I'm going to do that. Now I've brought that, I'm bringing the positive side of the 5 volt supply through to the rail eventually. I brought it to the middle pin of the switch. Now the upper pin, which is connected when I push the slide switch up, but the upper pin is bringing it over to this node, and that's where I can now put my thermal switch. So the thermal fuse. So this fuse is going to drop right in, if you can see, to this other, drop it right in there. Maybe I can do a side view for you. You see? So I'm bringing, now I've brought the positive side of the 5 volt source, through the switch, well, when it's up, and over to here. And the thermal fuse is, I'll bend that over a little bit. Thermal fuse is bringing it to this top node here. And I'll take it from the top node right up to finally what's going to be the 5 volt bus. So I do that with a couple more connections here. Yep. And again, needle nose work pretty good to get it in place. And you can see I'm just making that final, I don't know if you can see very well, final connection up to the upper rail. Okay, so we'll get that done. And then I'll zoom in. I'll finish these and zoom in a little bit. Oh, the other connection I have to make is, don't want to forget to bring the positive 5 volts to the other side of the LED indicators. They only have the 0 volt side connected, but they need to be able to indicate when 5 volts is on these rails. So I need to bring that positive voltage down to power up the LEDs too. So let me do that. Okay, there it is. I think it's all done now. We can test it out. If you're totally new to breadboarding, I don't know that I'd put this at a beginner level maybe. It's a little bit intermediate because of the tightness of some of these parts and pieces. But in the end, I think if you can manage it, do your best. But it's all about neatness and not letting things bump into each other. Here we've got our pre-cut jumpers, Of course, I was extra cautious. This is a bare wire coming off of the resistor here. So I made sure that I have, the green wire in place. I don't want to be bumping into that bare wire coming in from the resistor. But if you can see the connections, hopefully you can. The resistor is bringing the 0 volts to this side of the LEDs, this node, and the green pre-cut jumper is bringing the positive 5 volts to this side of the LEDs. And remember, the LEDs are put in opposite of each other so that, you know, the green light will light as long as the red bus is positive. The red light will light if by accident the blue bus is positive, in which case you have to straighten that out. And if you can see, we're bringing the red wire is bringing the positive side of the 5 volts to the switch. That's the middle pin of the switch. The upper pin of the switch is here. And I ran out of node, so I had to jumper it over to this node. And now I bring it through a thermal resettable fuse, which can carry 500 milliamps and blow at 1 amp. Or not blow, I keep saying that, but open up. And then the other side brings me right to the 5 volts, finally arrives at the rail. This is just a monitoring here, these two connections, the resistor and the green wire. They're not bringing power anywhere, they're just sitting there watching the power on the buses. And if you forgot, I can slide this over. There's the 0 volt connection coming straight from the power supply. It just comes right over to the blue bus. So I think that's the whole thing. Don't forget to put your little plastic feet on the back side of the breadboard. And sort of like I said, look at a dice, you know, the number 5 on a dice, put one in each outside corner, one in the middle. That just keeps the screws on the back of the breadboard from scraping up things and gives you a little better thing for the breadboard to sit on. Okay, well, it plugged in the wall transformer, the 5 volt supply. So now throw the switch, and looks like I've got my 5 volts on that bus, but at least the green light's telling me so. And it's the right polarity again. And I can turn it on and off. So lots of work for something that seems like, you know, I don't know, does it seem like a lot? Not really. But very useful, and hopefully you have a nice high integrity connection to your breadboard that'll serve you for the 2 years. And also I mean, this video was long, got real long, but I think it does a good job of tying everything together. It gives you a nice look at how everything's intertwined, the theory that you learn combined with actual trying to make something. So the making of anything always, you'll see that your time spent with theory is time well spent, and it's necessary. So hopefully this helped you, and I think it'll also help you. Maybe it's your first time breadboarding, so kind of did a baptism by fire a little bit. That's some intricate stuff to get in place, but I think we introduced a lot of things. And you know, one final thing, my technician instincts are telling me that green light's nice, and it's kind of a go, no go, or a nice quick indication that things seem to be okay. But I'm going to use my meter because that's what I really like, to tell me the whole story. So I can take this and, you know, use my nice little breadboard probes. I've got the other side's banana jacks going right into my meter. This is how I really have confidence that everything's exactly what I think it is. So I'm putting that on volts DC. Now watch, I didn't turn the switch on. You might be like, what do I have, 100 volts? Don't miss the milli, that little milli. So this is millivolts, and it's just noise, electromagnetic radiation, you know, around in the air, crashing into the breadboard. We'll get into all that. But so there's just millivolts, maybe 0.1 volts, nothing to speak of. But now I'm going to throw the switch, and I'll see the green light, of course. But there you go. Now I feel like I'm confident that I've got my 5 volts. And the correct polarity too. Okay, 1 hour on the nose. Long video, but I'm happy we introduced so many things.